Good evening, students. So, we are continuing with atomic structure, and in the previous session we enjoyed some facts about light, electromagnetic radiation, and the ranges of different electromagnetic radiations, visible light. On the higher end, you have got beyond violet, you have got ultraviolet, X-rays, gamma rays, and cosmic rays. And at the lower end, below red, you have got infrared radiation, and then microwaves, radio waves, all those things with greater wavelengths, less energy. And we also appreciated different wave properties and wavelength, wave number, frequency, velocity of all electromagnetic radiations are fixed. And we had a brief talk about energy of radiations, saying that each body emits radiation in the form of packets, quanta, which we will discuss in detail in quantum theory. So, we also calculated energy of electromagnetic radiation. See, lambda is the wavelength, nu is c by lambda, and we have done nu bar is 1 by lambda, and we have done energy of a radiation is h nu, because nu is c by lambda, h c by lambda, and this can also be written as h c nu bar. Once you know one information about any electromagnetic radiation, you can almost work out many things. And in these calculations, you have got two constants, very popular constants. One is velocity of light, 3 into 10 power 10 centimeters per second, 3 into 10 power 8 meters per second. The other one is Max Planck's constant, 6.63 into 10 power minus 34 joule seconds, or 6.63 into 10 power minus 27 erg seconds. So, these are the facts which we discussed earlier, and also we have done how to calculate the energy of a photon, which is a very less value, and 1 electron volt is 1.602 into 10 power minus 19 joules, or 1.602 into 10 power minus 12 ergs. So, this is what we could learn about light, assuming light travels in the form of waves, and also we have also considered this to calculate energy of a photon. That also we have learnt how to do it. But what for we have learnt all this? Why should we learn about light? I repeatedly told you to understand spectrum. And what is a spectrum? That we will work out in this class. Actually, this word carries a lot of meaning as the atomic structure is concerned. As a matter of fact, as chemistry is concerned, the word spectrum carries a big meaning, because we cannot see into molecules and atoms. We always analyze the signals given by what molecules and atoms. Those signals are captured on a proper medium, and we get some patterns. Analyzing those patterns, we will try to understand what is there inside an atom. So, atom is so small you can't see, and the activity of atom gives us some signals. Those signals we can call a spectrum. A recorded impression of a radiation emitted by an atom or a molecule or a sample. From any sample, you just get some radiation. You record it somewhere. That is called a spectrum. And I think most of you must be learning this word. I think you might have heard at a very early stage of life by saying that VIBGR, violet, indigo, blue, yellow, orange, red. It is a recorded impression of 7 colors or 7 radiations which are packed in white light, beam of white light. So, if you have any source of white light, it is a beam, if you can just split it into through a prism, like what is the job of a prism? It is an analyzer. It will divide the radiations as per the wavelengths, and they go in their own path. You just record them on a photographic plate which is photosensitive. You can see the impressions formed on it. So that is called a spectrum. Now here the $1,000,000 question is, who is the sample? How to obtain a spectrum of an atom? So that is the question. Actually in spectra, in broad sense, we have got two varieties. One is emission spectrum, another is absorption spectrum. Emission, absorption. What do you mean by emission? Giving out. What do you mean by absorption? Taking in. What do you mean by spectrum? A recorded impression of a radiation. So, what could be emission spectrum? Impressions of emitted radiation. Impressions of emitted light, impressions due to emitted light. Here the impressions are due to absorbed radiation. You may have a doubt, how absorbed light can give an impression? If light emitted from a sample, you can catch up and get the impressions, but how absorbed light give impressions? So there is a technique. The impressions are due to absorbed wavelengths. So some wavelengths will be missing in the spectrum. Why they are missing? Because the sample has absorbed. What do you mean by sample? The substance whose spectrum you are taking is a sample. You would like to take a sample and get its spectrum. I want to get iron spectrum. I want to get gold spectrum. I want to get silver spectrum. I want to get sodium vapor spectrum. I want to get carbon dioxide spectrum. I want benzene spectrum, ethanol spectrum. So it can be a molecule, it can be an atom, whatever. Excite it. If you excite it, no system can stay in excited state for a long time. How long can you be with angry? You will be cool all the time. Most of the time you will be cool. Rarely you become angry. At that moment you are excited and you shed out your anger and come down to normal state. The similar way, if you excite a system, an atom or a molecule, it will start emitting radiations according to its unique structure. Those radiations you pass through a prism and then capture on a photographic plate. You can see some impressions. That is emission spectrum. How to get absorption spectrum? Let us pass a beam of radiation into the sample. Beam means what? Large number of wavelengths. You take a good range of wavelengths and pass it through the sample. Few wavelengths are absorbed, remaining wavelengths are let out. So the remaining wavelengths fall on the photographic plate and spoil the entire photographic plate except at few places. Why not at few places? Because in those places the wavelengths are absorbed by the body. So the wavelengths are not recorded on the spectrum because those wavelengths are absorbed by the sample. If I show it in the board, you can understand. So emission spectrum is due to emitted light. Absorption spectrum, the impressions are due to absorbed light. So let us see. Suppose my sample is in this tube. Sample. Sample means what? Whose spectrum you want, that you take. and you subject this to electric discharge, apply high potential voltage. So, when you apply high voltage on the sample let it have atoms or molecules whatever, they start getting excited. I have been using one word, excitation. What do you mean by excitation? For any vibration there will be different energy states. See, my hand is vibrating like this slowly, it has some energy state. See, it is vibrating fast with a greater frequency, so it has got higher energy state. Still I vibrate, it is still a bigger state. So, different states slowly, very low energy state, these are called states. Any vibration corresponds to energy state and the frequency can be increased, then we say it is excited. How to excite it? Supply some energy. If you say apply some energy to a system, it will undergo excitation. Once it gets excited, it will come back after some time. While coming back to normal state, that is called ground state, the sample will start emitting radiations. So, when you start exciting the sample, radiations are emitted by the sample. Which radiations? Different radiations, means with different wavelengths, various wavelengths, lambdas, lambda 1, lambda 2, lambda 3. Those lambdas are decided by the structure of the sample. All samples will not give same lambdas, and this set of wavelengths is unique for that particular sample. So, these lambdas are to be analyzed, pass them through an analyzer, you call it a prism, whatever, grating, some fellow who can split the radiations, medium is called analyzer, and it will analyze the radiations into different wavelengths. So, you will get a line here, some line, some impression. This is an impression. This is photographic plate which is completely dark, but somewhere in between it will become bright. Why has that point become bright? Because light has fallen, and these impressions are due to what? These things. So, this impression is due to lambda 3, this is due to lambda 2, this is lambda 1, lambda 3, lambda 2, lambda 1. So, who is giving that lambda 1, lambda 2, lambda 3? Excited sample while coming back to ground state emitted those wavelengths, and those wavelengths are captured on a photographic plate, and on that photographic plate some impressions are formed. Because those impressions are due to emitted radiation, we call it emission spectrum. The recorded impressions due to emitted radiation is called emission spectrum. Now, how to get absorption spectrum of a sample? Do not excite the sample like this, do not excite, pass light into the sample. If you subject the sample to electric discharge or heat, it will get excited, while coming back it will emit radiation. But if you pass a beam of light, this is your sample. Now, I will not keep any voltage, anything like that. I will just send some radiations. I will take a bulb, different wavelengths I will send. This is a beam. The beam of radiation has got many wavelengths, lambda 1, lambda 2, which will not harm the structure of the system, and those wavelengths will pass through it. Some of the wavelengths are absorbed. Suppose this beam has got lambda 1 to lambda n, this many radiations are there. in that beam, but this sample will absorb lambda x, lambda y, lambda z. 3 wavelengths the sample has absorbed for its excitation, for its purpose, whatever you call it, but the remaining all lambdas will come out, all will come out. So, big beam will come out, and even if you pass it through a prism, all the beam will come out, and the entire photographic plate is affected. Entire photographic plate becomes white, bright, because so many radiations have fallen. But in some places radiations will not fall. Where is that? So, the entire plate is affected except some regions will remain dark. Why some places remained dark? Because there is no light has fallen. If there is no light falls on it, that remains dark, lambda x, lambda y, lambda z. Why some regions of the photographic plate are not affected? Because corresponding radiations have not come there. They are absorbed by the sample. So, now the marks are because of what? The distinct marks are because of missing radiation, absorbed radiation. So, the spectrum is called absorption spectrum. The spectrum is called absorption spectrum. So, if you want to get absorption spectrum of a sample, you pass a radiation through it. The sample will absorb some wavelengths and emit rest of the wavelengths. And on the photographic plate there will not be impressions due to missing radiations which are absorbed by the sample. So, we call it absorption spectrum. Whereas, when you subject the sample to electric discharge, the excitation will take place. During de-excitation, the sample will emit absorption. As a sample will emit radiations, you will get emission spectrum. So, this is how we get absorption spectrum and emission spectrum. If you want to get an emission spectrum, either you heat the sample or subject the sample to electric discharge. If you want to get absorption spectrum, you pass a beam of light into the sample and let some wavelengths be absorbed. The remaining light is sent on to the photographic plate. On the photographic plate, there are some impressions formed due to missing radiation. So, that is called absorption spectrum. Again, what is the sample here? That we should worry. What is the sample? Sample contains what? Now, this sample is excuse me, atoms. Free gaseous atoms. Why will an atom get excited? What do you mean by excitation of an atom? What will happen in an atom to get excited? Atom contains what? Who are the most mobile entities, particles in an atom? Electrons. So, electronic vibrations take place. Atoms always correspond to electronic vibrations. Once vibrations are there, there will be energy states, low state, high state, high state, high state, high state. Just I am showing a state with a small line. So, electrons may get excited into higher states like that, while they fall back to ground state. What will happen? They must lose energy. The energy lost by those electrons will be the radiations which cause emission spectrum. So, these radiations will come out, prism, photographic plate and line. A sharp line is formed for every radiation. because unique radiation, a single photon will come with a perfect single wavelength. So, because it's a single wavelength, a sharp line you can see in atomic spectrum. The nature of the spectrum depends on nature of the sample. The sample consists of atoms. What is there to excite in an atom? Nucleus will not get excited. Protons and neutrons will not get excited. So, only electronic excitation should take place. And atoms are free in the tube. So, each atom will excite. Each atom got excited means electrons only got excited. And those electrons when de-excited, there will be difference in the states of the energies, and that difference in the energy will come out in the form of photons, radiations, and those radiations contain unique wavelengths basing on the type of the transition. That unique wavelength will give a nice, beautiful, bright spectral line. And is it emission spectrum or absorption spectrum? Again, that depends on how you get the spectrum. Suppose you take atoms and subject it to electric discharge. The atoms get excited, and the excited atoms will start emitting radiations. And those radiations can be analyzed like this, and you will get a spectrum. So, atomic spectrum will always consist of sharp lines. Sharp lines will be there, and such spectrum is called atomic spectrum. And that is also called line spectrum. Atoms always give line spectra, clear gap between the lines. That is where we rejected Rutherford. Had Rutherford model been correct, electrons should lose energy continuously. No states are defined in Rutherford model. There will be energy states. Between the states, transitions take place and photons are emitted. Though each photon has a unique wavelength, and that wavelength will give a sharp spectral line. So, my dear students, always remember atoms give line spectra. Hydrogen gives hydrogen line spectrum, sodium gives sodium line spectrum, potassium gives potassium line spectrum. Whatever you gaseous atom you take, it will produce its own spectrum. Now, what about molecules? Suppose this contains molecules. What are all those? Molecular sample. What is a molecule? Suppose I will take acetic acid molecule. Acetic acid CH3COOH, very famous, you must be knowing. What does this contain? Bonds. CH bond, CH bond, CH bond, CC bond. You have CH bonds, you have CC bonds, you have C double bond O, you have C single bond O, and you have got OH bond. See how many varieties of bonds are there? 1, 2, 3, 4, 5. Different varieties of bonds are there. Molecules contain bonds. So, the bonds would vibrate. Suppose you have got carbon dioxide. It vibrates like a spring. It vibrates like a spring. It vibrates like this. So, there will be energy states, and the vibration need not be along the bond length. Sometimes the vibration will be along the bond angle. You just check this bond. There is an angle here, theta. Even that angle is also not fixed in a molecule. That also bonds vibrate like this. There are bending vibrations. Water. and most of you will tell 104 degrees 28 minutes. That is an average bond angle, not fixed bond angle. The bond angle is also not fixed, because bonds vibrate like this. They are all electronic systems. They keep vibrating. Charged particles. They can't be rigid. There will always be vibration. Another bond vibrates. So there can be vibrations along the stretching, bond length, stretching vibrations. There can be bending vibrations. There can be rotational vibrations. Molecule can show many phases. For each vibration there will be energy states. For this, one set of energy states. For this, one set of energy states. For every vibration there will be some energy states. They can get excited and de-excited. So how many wavelengths will come out at a time? And this vibration, this vibration, this vibration, this vibration, this vibration need not have same energy. The bond energies are different. So vibrations require different wavelengths. So generally when molecules are taken as sample, lot of wavelengths will come out. Close wavelengths will come out. Very close wavelengths. Because they might have similar energy, similar wavelength may come out when it is excited. So when these are captured on a prism and then on a photographic plate, you will see bands. So if your sample contains molecules and subject this to electric discharge, so many wavelengths will come out, passed on to the prism, and this prism will emit various radiations. These radiations will fall on a photographic plate to form bands. Excuse me. You will see some bands there, not like atoms. Atoms give sharp lines because they are electronic excitations. Molecules give bands because they are due to bond excitations. Many wavelengths will be very closely related and they will come out and form a spectral line. So close wavelengths will fall on the photographic plate. You will see a wide bands. This is called a band spectrum. Bands are due to molecules. So molecular spectrum. So my dear students, if the sample is gaseous atoms, you will get sharp lines in the spectrum. If the sample is molecules, you will get band spectrum. Line spectrum and band spectrum are due to the sample. Whether you get absorption spectrum or emission spectrum depends on how you get the spectrum. Emission spectrum is formed when you excite the sample, you heat it, or you subject the sample to electric discharge, you will get emission spectrum. Whereas you pass a beam of light into the sample, few wavelengths are absorbed, rest of the wavelengths are emitted, then you will get absorption spectrum. So whether you get emission spectrum or absorption spectrum depends on whether you are using the way you get the spectrum. Electric discharge and heating will give emission spectrum. Passing a beam of light into a sample gives absorption spectrum. If the sample contains only atoms, free gaseous atoms, single atoms, you will get electronic excitations, and because of that you will get line spectrum, sharp lines, atomic spectra or line spectra. And if the sample contains molecules, you will get bands, we call it band spectrum or molecular spectrum. Suppose you heat a solid, what will happen? I take a solid iron piece, I heat it, it will start emitting radiations. And these radiations are due to what? In a solid, particles won't move anywhere. There only the vibrations occur from their mean positions. There may be electronic vibrations, there may be molecular vibrations, there may be atomic vibrations, ionic vibrations. So many waves will come out, many radiations with different wide variety of wavelengths. Why? If you heat an iron piece, it will become red hot, white, red hot, then white hot, then blue hot. When it becomes white hot, you pass a white light onto prism, you will get a continuous spectrum, WIPGR. So solids always give a continuous spectrum. So when a solid is heated, you pass the radiations over a prism, you will almost get a continuous spectrum. Spectrum will be continuous. Atoms and molecules give discrete spectra. There will be, between signals there will be gaps. In solid spectrum, you will not have any gaps. Almost continuous wavelengths will be recorded on the photographic plate. So this is how this particular spectrum gives you a lot of information about an atom. So we have to develop such atomic models which can explain these spectra. That is why we rejected Thomson model, we rejected Rutherford model, we rejected, there was some other model which cannot explain. Between Bohr, after Bohr we will have Sommerfeld, that also could not explain fine spectrum. Bohr's model could not explain sodium spectrum and all. So unless a model explains all spectra, we won't accept a model. That is why we have learnt about light, now we have learnt about spectrum, now we will go to models, whether that atomic model can explain the spectrum or not. So that we should understand. Now let us visualize how these spectra are formed. What is a continuous spectrum? The spectrum of sunlight. If you take sunlight, white light, pass it through a slit and through a prism, you will get WIPGR. And in that WIPGR, violet means what? It is not a single wavelength. There are a range of wavelengths which will appear violet. Indigo, a small range of wavelengths. WIPGR. Blue, a small range of wavelengths. Green, range of wavelengths. Orange, red, like that. Every colored light is not a single wavelength. It's a particular range will I will recognize it as with that color, blue, green, orange, like that we should see. So this is actually don't think it's a bulb kind of a thing. Only source of light is shown like that. See, it's a white light source. It is emitting white light, passing through the prism and generating the WIPGR. See, this is a continuous spectrum, recorded impression of radiation. This is white, that has fallen is white light. So the prism has divided the light into 7 colors, and violet, indigo, blue, green, yellow, orange, red. Is there any gap you are finding in between? No. So we call it a continuous spectrum. See. Light, slit, prism, spectrum. So this is the simplest scheme of a spectrometer. Spectrometer means source of energy, then an analyzer, then a recording medium like a screen where you can record the impressions. So it's a recorded impression, continuous impression. So we call it a continuous spectrum. All solids are, because white light is having just 7 colors. There may be some solids which you heat will give a continuous spectrum, like black body, we will discuss later. Now just see how to get an emission spectrum. What did I tell you? To get an emission spectrum, sample is to be excited. So how it is to be excited, we will see. See, there is a discharge tube. In that tube, we have got all atoms. See, you are seeing the yellow color. Yellow atoms are excited atoms. Orange atoms are normal atoms, ground state atoms. Because electric discharge is given, the light is coming and the spectrum is formed. I will repeat. Observe carefully. See, I am just subjecting this to electric discharge, high voltage. So, some atoms got excited, emitted light, prism, some radiations are falling, you are getting sharp lines. See the color of the photographic plate, black. Light is, lines are white, bright white. Line spectrum. So, because these are atoms, see, these are normal atoms, these are excited atoms. The excited atoms are emitting radiation according to their structure, and those radiations are analyzed by the prism and you are getting sharp lines. These lines will decide the structure, lambda x, lambda y. Where you find some bright lines, wherever light has fallen, there the photographic plate becomes bright. So, the energy emitted by the atoms are forming this, so we call it emission spectrum. See, from these bright points, radiations are coming. Radiations. All these radiations are going through the slit of the thing. These radiations contain different wavelengths, and one has gone here, one has gone there. You have got the lines, and all will not have a unique spectrum. Different atoms will give different varieties of spectrums because their atomic structures are different. That is the beauty of spectrum. So, I have just excited, few are orange, few are bright. So, the brighter atoms got excited, excited atoms, they emit radiations. So, we got it emission spectrum, we call it atomic spectrum. We call it atomic spectrum because these are atoms. Because these are atoms, you got line spectrum. Because you excited it, you got emission spectrum, and this is also called line spectrum. Or you can call it atomic spectrum, like that. Sodium spectrum looks like this. At 5890 angstroms, 5896 angstroms. Means what? If you take sodium atoms and get the spectrum, you will find two bright lines like this. Even Niels Bohr could not explain why those lines are formed. That is a different story. Sodium spectrum has two bright lines. Hydrogen, if you keep hydrogen here, you will get hydrogen spectrum. That also contains lines like this. So many lines. Hydrogen spectrum. So, all atomic spectra look something like this. You know? Atoms, excited atoms, emitted radiation, prism, splitting, spectral line formation. Photographic plate is dark, spectral lines are bright. So, it is emission spectrum. Now, let us appreciate how absorption spectrum is formed or how molecular spectrum is formed. Instead of atoms, if I use molecules, as I told you, Atomic spectra will have sharp lines. Molecules, if I use in the discharge tube, there will be several varieties of vibration, several wavelengths are emitted. So, you will have bands formed. Bands formed, that also we will see. Spectrum having distinct and well defined lines gap, it is called discontinuous spectrum. Two types: absorption spectrum, emission spectrum. Absorption spectrum, emission spectrum. It is produced by transmitted light. Emission spectrum, emitted radiation. It contains dark lines, bright background. It contains bright lines, dark background. Emitted light gives emission spectrum, bright lines and dark background. Absorption spectrum is due to absorbed light. The entire photographic plate will become bright except one or two places where it remains dark due to missing radiations which were absorbed by the sample. That also we will see. See, now I am not subjecting, here I will keep now the sample and I will not keep any electric discharge. See, did I have any battery or voltage arrangement? Nothing. I am just passing a beam of light. I will just send light into sample. I will keep my sample here. So, the light will go into the sample with many wavelengths, many radiations, beam of light. The sample will absorb some of the radiations and the remaining radiations are allowed to fall on the photographic plate. You see what is happening. Light is falling on the atoms. See now. What did you observe? What did you observe? The entire photographic plate has become white. Why? Most of the radiations have fallen there. But some places it remained dark, where the radiations have not fallen. Where have those radiations gone? The sample has absorbed. So, sample, there are many lambda 1 to lambda n radiations are coming, but the sample has absorbed lambda x, lambda y, lambda z, lambda w like absorbed. The remaining radiations have gone and affected the photographic plate. The photographic plate is not affected in some places because lambda x, lambda y, lambda z are absorbed by the sample. So, we call it absorption spectrum. And because these are atoms, that is atomic spectrum only, atomic absorption spectrum. You see once again a beam of light passing through atoms, some of the radiation is absorbed, remaining radiation has gone through the prism, it has influenced the photographic plate except some places. At those places you have seen some dark lines. So, that is absorption spectrum. Why you got lines? Because atoms are present in the sample. If molecules are present in the sample, what will happen? Let us see. See, once you see the battery and discharge tube, what do you immediately understand? It is emission spectrum. Now, I am having molecules. So, because of molecular vibrations, what will happen? Bands. See, photographic plate is dark and the impressions are bands. A band is formed. See once again atoms, now molecules. Molecules. See, these are all molecules. Now discharge, radiation, you are getting bands. So, that is a band spectrum. See the beauty of formation of a spectrum. Had it been a solid, say I took a solid iron piece, I am heating it from the bottom. So when iron piece is heated, first it will become red, after some time it will become white, then it will become blue. So all radiations are emitted. When you pass it through prism, again you will get a continuous spectrum. See, heating. It has become red. It starts emitting radiation. Prism, spectrum. See, what is this? It's a continuous spectrum. There are no gaps like atomic spectrum. So atoms give discontinuous spectrum with sharp lines. Molecules gives discontinuous spectrum with bands, wide bands. And solids would give a continuous spectrum. Heated solids give continuous emission spectrum. Spectrum will be continuous. This is a continuous spectrum. Like this. So, my dear students, emission spectrum, line and molecular spectrum. Line spectrum, it contains sharp distinct lines. The characteristics of gaseous atoms, it is due to transition of electrons between energy levels in atoms. Electronic transitions give emission spectrum, line spectrum. Whereas contains merged lines called bands. Gaseous molecules give band spectrum. It is due to rotational, vibrational motions of atoms in molecules. In molecules, atoms undergo rotations, vibrations, stretching vibrations, bending vibrations. Many varieties of vibrations exist in a molecule. Therefore, many different wavelengths are emitted by the molecule when heated, and those wavelengths are closely placed, so we will get wide bands. So, atomic spectrum look like this, molecular spectra look like this, and solid spectra look like this. Solids give a continuous spectrum. WIPGR anyhow you know. So, among all the spectra, the simplest spectrum is hydrogen spectrum. Hydrogen emission spectrum. Just now I told you atomic spectra look give sharp lines. So, how to get hydrogen spectrum? How to get sodium spectrum? Keep sodium atoms in the discharge tube, then pass voltage, you will get sodium spectrum. If you keep hydrogen atoms in a discharge tube, you will get hydrogen spectrum. So, take a discharge tube, keep hydrogen atoms. How many? If you send hydrogen gas also, it will become atoms because you are applying voltage. Even if you take 1 gram hydrogen in the discharge tube, that will contain 6.023 into 10 power 23 atoms. 1 gram hydrogen contains 600 crore atoms will be there in the discharge tube. 1 gram. So, that is so many hydrogen atoms will be there, and you are supplying electric discharge voltage. All hydrogen atoms will get excited. I told many times, what do you mean by excitation? Atoms undergo electronic excitations, electronic vibrations. So, electrons will go into some upper states, the states we do not know by now. We will see later after hydrogen, Bohr's model and all. Let us now just take states are there, energy states, low energy state, high energy state, still high energy state. So electrons may get excited into different states. You may ask, how many electrons, how can there be so many electrons in hydrogen atom? And all these incidents are not happening in one hydrogen atom. You have got crores of hydrogen atoms kept in the discharge tube. In each hydrogen atom there can be some kind of excitation, and in some other hydrogen atom some other kind of excitations. So the excitation extents may vary from atom to atom, and while they are coming back to normal state, they start emitting various radiations of different wavelengths, lambda x, lambda y, lambda z. And those wavelengths form spectral lines. And the most beautiful aspect of hydrogen atom is the simplest spectrum, but it will contain so many lines other than other atomic spectrum. Sodium spectrum contains just 2 lines, but hydrogen spectrum contains hundreds of lines. I mean, so many lines closely packed. May not be 100, I would like to say so many lines, series of lines you will see. Now let us see. You take hydrogen gas, so all H atoms are there, subjected to electric discharge. So many radiations would be emitted due to hydrogen atoms coming back to ground state and pass through a analyzer. You need not be prism, it can be any analyzer that will split the radiations into different wavelengths. And if you see the spectrum, you will find so many series of lines, different series of lines. The gap between those series also will not be uniform. You will get different series of lines formed, and one is formed in ultraviolet region, one is formed in visible region, some infrared region, some other infrared region lines you can find. This is how a hydrogen spectrum looks. So the people could do this experiment. They got the spectrum, but no idea about atom. No one knows what is the atom. Structure of atom was not known. So what might have happened in hydrogen atom? But definitely once spectral lines are formed means some radiation must fall. That too, it is an emission spectrum. So how do you know that the radiations would come? Due to emission of radiation from atoms. Why atoms emit radiation? Because atoms contain only electrons. Might be the electrons got excited into different states. So there may be some states in the hydrogen atom, different possible positions for an electron to occupy. So in those states, if the electronic transitions take place, electrons while falling back to ground state, they would emit radiations, and those radiations will form spectral lines. So one wonderful equation was worked out, Rydberg, which is on empirical grounds, just like that, trial and error grounds. He worked out, and he got an expression to calculate the energy of these radiations, correlate these radiations, and that expression is called Rydberg equation. This is actually nu bar, which is 1 by lambda, is equal to RH into 1 by n square minus 1 by n2 square. Without any mathematical approach, it was just basing on the wavelengths of the lines, it was guessed. With some constant value, empirical relation he obtained. This nu bar is what? Wave number. This is wavelength. Whose wavelength? Whose wavelength? The wavelength of the radiation which gave a particular spectral line. Suppose in the hydrogen atom, hydrogen spectrum, there is a line. Why is that line formed? Due to some radiation. Why that radiation is emitted? Due to a transition. What do you mean by transition? Jumping of an electron. Where from to where? From one state to other state. States are not known. States are given some numbers. First state, second state, third state, fourth state, like. So, hydrogen would contain some energy states. As I told you, for every vibration there will be a set of energy states for every electronic vibration. So, basing on, suppose electron is jumping from here to here, 1, 2, 3, 4, 5, like that, you give random numbers. Numbers are not having any significance by the time hydrogen spectrum was known. Later, Niels Bohr model gave what are those numbers and verified the value of this constant. When hydrogen spectrum was given, people did not know what is N1, what is N2, just random numbers. So, when they correspond to some numbers, based on the gap, based on what is N1, the region in the spectrum is decided. That we will see now. Suppose, and what is this RH? This is a constant called Rydberg constant, 109,677 centimeter inverse. Why should it have centimeter inverse units? This has no units, that has no units. This is centimeter inverse, 1 by lambda centimeter inverse, so it is centimeter inverse. RH has centimeter inverse value. Now let us see. Suppose there are some states in hydrogen atom like this. Don't call them anything, some states, that is it, at present. After 2 classes, we will give them beautiful names later. Right now some state, state 1, state 2, state 3, state 4, state 5. And electrons are at random may get excited into various states, higher states. You do not have a single hydrogen atom. You have got lakhs of hydrogen atoms, crores. And if I throw chocolates into a classroom, different students may get different number of chocolates. All need not get same number. One may get 10, one may get 8, one may get 2, one may get 1, one may get none. In a similar way, when electrons, hydrogen atom get excited due to electric discharge, in each hydrogen atom that single electron may get excited to different energy states, and while coming back, it may come stepwise, it may come direct, different varieties of transitions may take place, electronic transitions. And if at all any electron falls from any higher state to first state, very high energy is released, because you are almost coming into the first state, and such line, such transition would give some radiation H nu, and that radiation gives an ultraviolet light. Why will it give ultraviolet light? Let us verify. Just now I gave a formula, nu bar or 1 by lambda is equal to RH into 1 by 1 square, N1 square minus 1 by N2 square. From any higher state, if at all electron jumps into first state, so 1 by lambda is equal to RH into 1 by 1 square minus, let me take it as 2, 1 by 2 square. What would I get? RH into 1 minus 1 by 4, that is 3 by 4 into RH. But what is this 1 by lambda? So, what will be lambda then? 4 by 3, 1 by RH. My dear students, 1 by RH means what? 1 by 109677 centimeter inverse. You will get some small value in centimeters because it is 1 by centimeter inverse. If you multiply that with 10 to the power of 8, you will get in angstrom units. This value will be 912 angstroms. So, reciprocal of RH is always, you can take it as 912 angstroms. So, what would I get? 4 by 3 into 912. This goes 304 times 1216, 1216 angstroms. 1216 angstroms is the wavelength. What do you understand from this value? That is the wavelength of a radiation coming out of an hydrogen atom due to dropping of electron from second state to first state. And what is this 1216? And in the previous class, I gave you electromagnetic wave spectrum. In that wave spectrum, we have decided from 3600 to somewhere around 7800 or 3800 to 7600, it is visible light. But this is below 3600. And this comes in the range of ultraviolet light. Ultraviolet light. So, whenever electron jumps from 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, 7 to 1, if at all electron jumps into the first state, you will always get different wavelengths that range in the ultraviolet light only, and such series is called Lyman series. And if at all electrons are falling into 2, and all these radiations will give visible light. How do you say you will get visible light? Let us see. Suppose electron is jumping from third state to second state. Third state to second state. So, 1 by lambda is equal to RH into 1 by 2 square minus 1 by 3 square. So, RH into 1 by 4 minus 1 by 9. So, this is 36 LCM. 36 LCM, 9 minus 5, 4, 5 by 36. So, what is lambda? 36 by 5 into RH. Just now I told, sorry, 1 by RH. Just now I told 1 by RH value is how much? 912. And this approximately goes 35, 7. 7 nines are 3600, 3684. 3684 comes under visible light. So, whenever electron jumps into 2, you will get visible light, even from infinite level to 2 also. So, my dear students, suppose free electron is falling into second state of hydrogen atom. So, what will be the wavelength of the radiation? What is lambda? So, how to calculate lambda? Lambda is equal to RH into 1 by second square minus 1 by infinity square, and this is going to give me this is 1 by lambda, RH into, this is 0, 1 by 4. So, what is lambda? 4 by RH, 4 by, so 4 into 912. So, that gives me how much? 3648. This is visible light, somewhere around violet. So, whenever electron jumps from anywhere to second state, you will only get visible light. If at all electron jumps from any higher state to third state, you will only get infrared light. If at all electron jumps from any higher state to first state, you will only get ultraviolet light. That is the reason in hydrogen, and all the things need not happen in a single hydrogen atom. May also happen. Suppose in a single hydrogen atom, as I said, there may be many states. Electron may jump stepwise like this. In each step there will be a particular wavelength radiation is emitted. That is the reason you will have so many groups of lines formed in the hydrogen atomic emission spectrum. I think you will appreciate this hydrogen spectrum more after we complete Bohr's model. In this is a rather an empirical expression. 1 by lambda is equal to RH into 1 by N1 square minus 1 by N2 square. Actually, N1 and N2 are not well defined quantities, random values. It must be whole number, random values. And RH is randomly worked out, but very successful, wonderful effort by Rydberg. So, we have got a Rydberg constant 109677, and this value happens to be correct after we prove it after Bohr's model is done. So, if you get a hydrogen emission spectrum, it looks like this: Lyman series, Balmer series, Paschen, Fund, bracket, that many Humphrey. Different lines are due to different radiations coming from different transitions happening in hydrogen atoms. See, if at all electron jump from any state 2, 3, 4, 5 to, don't ask me what are those states at present. We know only spectral knowledge, we do not have atomic knowledge, that we will get later. If at all higher state is 2, 3, 4, 5, the lower state is 1, you will get a series of lines. Those lines will have lot of energy, so you will get it in ultraviolet region. If at all electron jump from any higher state into second state, you will get visible light, near infrared, far infrared, and the series are called Lyman series, Balmer series, Paschen series, bracket series. At present, my dear students, I will give you a beautiful advice. Never think 3 to 2 transition and 2 to 1 transition will have same wavelength, because the gap is same. 3 to 2 is different, 2 to 1 is different. Do not be carried away by the numerical difference between 3 and 2 and 2 and 1. Anyhow, the difference is 1 only, here the difference is anyhow 1. So, do not think because 1 is the difference, the spectral line will be same. Do not think like that. 3 to 2 gap is different, 2 to 1 gap is different. All these with quantities of values, energies, everything we will calculate, quantitative approach. Right now we are just giving spectrum description. We do not do anything right now. Once we finish Bohr's model, we will come back to hydrogen spectrum again. We will do so many problems and their physical meanings of energies. So, my dear students, we enjoyed so much on spectrum, thoroughly we have discussed. Continuous spectrum, line spectrum, band spectrum, atomic spectrum, molecular spectrum, emission spectrum, absorption spectrum, solid spectrum. We have done hydrogen spectrum, sodium spectrum I have seen. So, spectrum is the evidence for atomic structure. So, now we will focus on some other beautiful aspect of light, that is black body radiation and Planck's quantum theory, followed by Albert Einstein's photoelectric effect. In the beginning classes I gave you a hierarchy, just follow that hierarchy, you will understand what I am going to teach in next classes. Thank you so much, enjoy, we will keep meeting, have a good day, see you.